Hello, I'm going to be doing the Alkene review. I apologize for getting this video out to you guys late. When I first did this video, I got a lot of the answers wrong because Grubbs is the person. We all know who he is. So I'm going to do it again. Again, I apologize, but I have the key now and I understand the problems I got wrong and I understand what he wants from you guys. This video will be much better than me making it on that. Okay. So first things first is we're going to have to draw these structures out. One thing you guys going to notice is this E and this S. These are going to tell us what to draw. So this dibromo is referring to this 3 and 5. This hexane right here is referring to this 2 right here. I also apologize. I'm drawing in with my mouse today, so it's going to be drawing's been much worse than normally they are. But that's what we're going to do. So hexane, the E means double bonded. So we're going to draw some bonds. So 1, 2, double bonds be here. 1, 2, 3, and then 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay, there we go. And then there we go. That part's done. That part's done. The dibromo. So let's do the 3 first. Because this right here, E, remember E basically is equal to trans. We're going to make this molecule trans in regard to the biggest molecules attached to the bond. That would be, in this instance, a bromine and this methyl group right here. So once it's attached to this guy right here, what's going to occur is it's actually going to go straight up. You're going to get a bromine group like this. And what this does is this kind of makes a molecule trans-like, which is right there. Up next is going to be the 5 bromo. And that would be 1, 2, 3, 4, 5 right here. In this case, the key makes it a dash. And the reason being is because Grubbs from now on is going to want to make you put stereochemistry in all chiral molecules. This carbon right here is chiral, right? It is connected to a methyl group, a hydrogen, and a CH2 group. So it being like that, it's going to do stuff like that. 1 second, as soon as I ask for questions, I will be right. Okay, sorry, my bad. I actually noticed something too when I came back. This right here would actually not be a dash. I drew my molecule the right way, Grubbs drew his backwards. So actually, technically, if you draw it this way, the molecule actually will be a wedge. It's because this is the highest part of the group. This carbon right here would be secondary. So it would go counterclockwise, it would be sinister. If you put a dash there, it would make it going to be an R group. So this is the first molecule looks like. The only difference between this molecule and the second molecule would be here. The bromine would be kind of going down a little bit. So that way it'd be cis. 1, 2, 3, 4, 5, 6. 5 going up here, it would still be a wedge structure. Okay, over here, same things can occur, except instead of having it be a wedge, it'd be a dash, 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 dash BR. This is what this one right here would look like. And the other one would look like this. You would just take this guy right here and make him go up. Reason why, again, we have him as a dash here, because this guy right here is chiral. And priority groups go 1, 2, counterclockwise, sinister. That's idea number 1. Okay, overreactions, we're gonna do this one right here. This one's a bit more tricky than I thought it was when I first saw it. But we have D and C. We're gonna treat D like a hydrogen. It's just not gonna be exactly like a hydrogen. It's gonna be a bit off. So when you break the hydrogen-chlorine bond, the electrons are gonna go towards the chlorine, making it an electrophile, making it negative. Well, D is positively charged. Remember that a double bond basically is a positive and negative charge next to each other. So when this molecule breaks, it's going to put the negative charge where it wants to be, which is near the end, right here. So negative electrons are here. The positive electrons are going to be on the most stable place right here. Add the chlorine, add the D part. The negative electrons here are going to be attracted to D. You're going to get positive charge here to a D. Now, this is the part I got confused with, and I had to look this up, but this right here is a methylene shift, not a methyl shift. So anytime a methylene shift is going to happen is you're going to break a ring structure and make a new ring, usually one that is more stable. Now, remember that the most stable ring is cyclohexane. So any molecule going up to cyclohexane, the closer to cyclohexane, the more stable you are. Here is cyclobutane. What is the next one more stable than cyclobutane? And that would be cyclopropane. So the bond here is going to break. So remember the positive charge here. And the carbon here is going to go bond to this guy right here. And this right here is going to make this structure. Make a cyclopentane, no house, and it should be a positive charge here, right next to the methyl group, and this guy just shifts over by 1. We're then going to add the chlorine group. Chlorine group comes to be added, so we can just get rid of the positive charge and add the chlorine, and that's what the C structure looks like. There we go. So it's always better to ignore the overall reactions and just do step by step. Do step by step to tell you. Because I did not know what methylene shift was, and now knowing it, it makes sense a little bit. 1 second. Here, number 3, we're going to be doing following some curved arrows. There are 2 boxes. Whenever there's 2 boxes in your classes on your exam, either means we're going to be making a racemic mixture, or we are going to be making 2 different compounds. In this case, we're going to be making 2 different compounds. So we have arrows 1, 2, 3, 4. Arrow 2 being the most important one, because what's going on here, arrow 2 is saying this bond right here is breaking. A double bond here is forming. Arrow 1 saying some electrons from here are going to be going to attach to this oxygen. We're going to take the electrons from this oxygen, from this double bond right here, use them to attach to this guy right here. So now we have an alcohol group here. And the bond that was here is going to attach to this chlorine. So what you're going to get is you're going to get oxygen, double bonded oxygen to an alcohol group attached to a CH3 group. You're then going to get HCH3, CH3, this is nice peroxide, which is a triangle with a little oxygen attached to it, and little hydrogens come out. Those are your structure you're going to get from that reaction. Okay. This one was confusing to me too, but we're going to do it step by step. First things first, ignore that it says sulfuric acid, just assume it is 1 hydrogen. The reason being is that this is it gets protonated by protonation of a hydrogen. I always assumed that since there's sulfuric acid, and protonate both of them, only 1 hydrogen deprotonated though. So this bond breaks, negative goes here, positive goes here. Since hydrogen is positive, it's going to protonate that 1 right there. So you're going to get this structure right here. The hydrogen gets attached to the negative side right here, and attaches and get that structure. You're going to add your water group, because the negative charge in the oxygen is going to attract to the positive charge, and you're going to get this occurring. Since oxygen is positive, since it has 3 bonds, it's going to break one of the bonds with its hydrogen. That bond's going to go here, release, get rid of the negative charge, which makes a free floating hydrogen, which gets picked up by excess water. And the last product you get is going to be Boom. That's what that product looks like. Okay. This part here, 2B, so we're doing methylene shift. So here's cyclopentane. What's the more stable one? That version is cyclohexane. So you're going to basically remove this bond right here, take this carbon and bond it up to there. So it should look something similar to your cyclohexane. There's your methyl group, and then coming off of it should be your positive charge right there. Same thing, you're going to add oxygen, same thing a step above, it's just a new structure. So there's your water, positive charge there, you get rid of the positive charge. I need an alcohol group going off right here. Cool. For some reason, Grubbs put the positive charge right here instead. I don't understand why. Even if we did, we would have done a hydride shift there. So his key has it where the purple one is, which means the water would be here. And the alcohol group would be here. I like where mine's at because that is the most stable place for a carbocation. What part C right here is saying, you want to do a hydride shift A. So going back to A right here, you notice the positive charge right here is on secondary carbon. In reality, it would want to be on a tertiary. So we're going to go here. There's your positive charge right there. Water. Remember, since oxygen has 3 bonds, it's positive charge. It's going to break one of its bonds off from its hydrogen, and then that's going to give you a alcohol group. There you go. So those are how you do step 6. 7's a bit weirder. 7 is, since our molecules are all like that, we're in the elimination part, which just means we're going to remove the water and add double bonds. So let's do the methyl groups. Let's do the hexanes first. So the hexanes. So that's what the hexanes look like, right? So once the water is removed, correct? The double bond can either go here, or the double bond can go here. And it is likely to equal ones. We don't know what E1 or E2 we're dealing with. So we're going to put double bonds on both. Up next, we have the methyl group like this, where the alcohol was coming off it like that, correct? So we can have the rest of them being based off of that, which means we get a double bond here. Double bond here. And lastly, you get a double bond here. And those are your 3 options. Okay. More importantly is number 8 is the first one that's going to definitely be under test right here. So this is using hydrogen with PDC right here with a cis molecule with branches. If using H2 hydrogen with PDC, which is a metal catalyst with branching, you're going to get a racemic mixture. And basically what's going on here is PDC is acting like a metal catalyst, which is the C right here. It's a metal catalyst. And what happens is the double bond here is going to cause this weird bonding circumstance in which it temporarily bonds the metal surface. And these branching can either stay and get kind of blocked off, in which case excess hydrogens can't attack correctly when you draw the hydrogen between colors, so you see all red, where hydrogen can come in and hydrogen can come in and they can kind of, I can draw black, come in and they kind of pop off these bonds to attach. If the branches are not pushed back, the hydrogens will act like dashes. If the branches are pushed back, they'll act like wedges. So basically you're going to get both. So you're going to get hydrogens. And dot, basically. Or you can get the opposite, in which we get hydrogens, 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 wedges, CH2, CH3, CH. 1 second. Okay, I am back. I'm going to rotate this page again, so now we're back to normal. Whoopsie daisy. There we go. Okay. Number 9 is also very, very important. Oh, someone has a question for me. Give me one. Okay, there we go. Sorry, I'm in class, making sure I'm helping, trying to get this video as soon as possible. So you guys have both videos out today. Okay, there is your benzene ring, bada bing, bada boom. Where NBS is going to put a bromine on the most stable carbon. It's because it forms a radical, and radicals are just like carbocations. They form they have a very similar stability chart. So, but since there's 2 of them, we're going to form a racemic mixture. So you're going to have a wedge for a bromine, or you're going to have. Also, you want to piss Krebs off, draw your benzene rings like this. He absolutely loves it. Good. Now, the most important part of number 9 is the next one right here. This right here is an anti-Markovnikov. So let's zoom in on it so we can look at it. So first things first, we're going to do the bonds, right? So this double bond right here goes away. And it usually is a positive and a negative charge. Now, normally what we'd want to do is we want to put the positive charge here and a negative charge here and call it a day, correct? However, that is not the case. Since this is an anti-Markovnikov reaction, we're going to do the exact opposites. We're going to put the negative charge where it doesn't want to be and the positive charge where it doesn't want to be. Just because this anti-Markovnikov, there's a whole thing with a less substituted carbon, the one with the fewer hydrogens, stuff like that. That part always confuses me because they're so similar to each other. Just know anti is the opposite of what we normally do. We try to make everything as unhappy as possible. So we put the negative charge where on a tertiary and the positive on a secondary. So a hydrogen's going to attach there and a bromine's going to attach here. Since they're being anti-Markovnikov, we're also going to get enantiomers of each other. We're going to get, racemic mixture. Because technically this carbon right here is chiral. So since the carbon is chiral for anti-Markovnikov, it's going to be racemic. So we're going to get an R and an S. So what would go here instead? The exact same setup, except instead of being a wedge, it's going to be a set of dashes. And that is what it looks like. Okay, this guy right here is also anti-Markovnikov. So got to get rid of this double bond. And we put the positive charge here and negative charge here, because the negative charge does not want to be benzoic or tertiary, it wants to be primary. But since it's anti-Markovnikov, we have to do the opposite of what we normally want to do. So we draw benzene, we draw next structure, and then since this guy right here is, this one I don't understand. This one should not be chiral. I don't know what he was getting at this one. So I don't know why there's it's a racemic mixture, but it is, even though technically there is no RNS, because it being there between hydrogens, it's in a primary carbon, it makes no sense. So then that doesn't make any sense, but that's what he put. That's what he put. I would argue only one box is needed because it's not chiral, but it is what it is. The reason why I say it's not chiral, for those of you who remember, is chiral needs 4 different molecules. If the bromine does go here, it is a carbon attached to a bromine, attached to a carbon, which is fine, that's 2. Then it has 2 hydrogens here, which would not be good for business. Yeah, it looks like this. Bromine, carbon, and then would have 2 hydrogens. So, not good. Okay, what's going on here is there is no delta on here. I thought it was a typo beforehand, but it's not. We're going to form radicals. 1 second, guys. Yeah. Hello, I'm looking back. Like I said, we will be doing. Hello. Make sure my headphones working. Sorry about that. Yes, we are going to be doing making radicals. So we're going to make a bromine radical. Sorry about that. My headphones were acting up, so I wasn't going crazy. Yeah, so when the bromine breaks, you're going to get 2 bromine radicals. And over here, you're going to break off one of the hydrogens. You're usually going to break off a hydrogen. So radicals like to go benzylic, allylic, tertiary, secondary, and primary. So you only have 2 secondary, so it's in a pick, toss up. You're going to break the bond between the hydrogen and the carbon, since they're very similar to each other and doing radicals. 1 gets 1 and 1 gets 1. So now you got this guy with a radical here and a hydrogen radical here. To make both bromines happy, 1 bromine is going to make an HBr, and the other guy is going to attach there. And since we have 2 boxes, it's going to be racemic. We're using being, it's racemic. This is Antonov-Kobnikov in regards to having a chiral carbon, which this carbon is definitely chiral. 1 second. So this guy right here is chiral. You can see that there's right there and right there the chiral carbons. It is bonded to a CH2, a CH3, and an H and a Br. So they are going to be racemic mixtures. For this guy right here, there's only 1 box because there's only 1 possible place, and it's not chiral. The bromine is going to attach here because that is the best place for a radical to form. So it's just simply going to be that guy right there. Okay. Number 10, what number 10 is asking us to do is it wants bromine to leave. So bromine's going to leave. At the same time, iodine here is going to attach. And typically iodine's going to act more like a push to kind of knock off bromine that comes in. So technically it's going to be a little bit of a wedge as well. Not going to matter too long because we're not going to keep it very long as it's going to leave. It's a leaving group. We have here is a bulky base, which means we're going to do an E2 reaction, which means we have 2 possible places. Double bond can go where the red is located, or double bond can go where the orange is located. So for bulky bases, we're going to be doing something called a Hoffman's projection, is what he hopefully taught you guys in class, which means you're always going to do the less substituted one for E2 bulky bases, which means you're going to make the red one because there is no methyl group there. So there's your Hoffman's projection. If you were to make an orange one, that would only occur for a very, very strong E2 base. And I forget what that one's called. It's something else, some other type of reaction by some other cool other guy named Hoffman. Yep, number of electrons here, number of arrows. Fun ones. Okay. So let's do different colors. Here, we're going to make step 2. So we have to make this guy right here. So to make that guy, arrow up here goes up here, which makes this right here negative, which makes this guy positive. Using the bonds of this guy, attaches up to here. 2 arrows. Okay, let's use pink next to make this guy right here. We got to do some steps. First off, these bonds right here are going to come up here, bond here. That's going to make this guy kind of negative. So we're going to kick off chlorine, make it positive, chlorine, and that's how we get this going right here. So 2 arrows. In this step right here, we're going to use green. Oxygen is positive, it is only positive, so we're going to break the bond of our hydrogen. Hydrogen becomes positive, and the amine group's electrons here are going to bond to this guy. Also, 2 bonds. So let me just erase some arrows. So now we're on the very last step, step 3 to step 4, and I'm going to use purple. So what happens here is oxygen is going to break the bond here. That's how we get this guy right here. That's going to make this guy right here slightly positive. To appease that, we're going to need to take a electron or hydrogen from this guy and make this guy negative. So it breaks the bond, makes this guy right here negative. That way we can form this double bond right here. The amine's also going to take this right here. You notice I only drawn 3 arrows. So that's 3. So 2 plus 2 plus 3 is a total of 9. So there are 9 arrows in general. Put those back on the screen for you guys. That's the very last one. Most within the videos, you can stop, replay, and kind of slow down. So the answer would be right here, would be 9. Okay. So this one right here is this POCl3. This guy right here is the same reaction as above. So we're going to look at both of them. Boom, 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 boom. Same reaction. So we're going to answer questions about that reaction. So 12 is going to be true. The reason being is we like POCl3 as a preferred reagent because of rearrangement with strong acids. Strong acids seem to rearrange things. POCl3 doesn't react with hydrogens, right? It didn't attack the H at all. So it's really good when we want to react with strong acids to get a certain product. This right here, actually, this one here is true. It made the OH leave, made a double bond, so that one is true because it did work. 14 is false. If you look at the equation above, we didn't protonate the alcohol at all. We deprotonated it and kind of pulled it away from it. So that one right there is false. Okay, so did not protonate. There is no hydrogen in this molecule right here, so it cannot deprotonate. And theoretically, 14 also, this guy right here, the amine is what deprotonates that one. And lastly, we do not really technically eliminate it. It is not just the POCl3, it is a combination of POCl3 and the amine that eliminate the hydroxy group. If we did not have this amine here, all we would have is this guy right here. It's the combination of both that do the job. 1 second. Okay, sorry about that. I had to talk to some people and had to transfer classes. Welcome back. So this concept, the heat of hydrogenation. So heat of hydrogenation is pretty simple when you think about it. What this thing is looking at is this guy right here is looking to see if we're adding hydrogen. Adding hydrogen to heat of hydrogenation. Hydrogenation is just a term for hydrogen. And the concept's pretty easy to think about it. Is The more stable a hydrogen molecule is, the less heat it's going to give off. So the more stable it is, the less heat it's going to give off. So 2 double bonds makes a molecule a little less unstable because it adds 2 kinks, and adding kinks into something makes it bad. Like adding kinks to a chain or something like that, it's not the best thing to have. So those 2 should be higher than this guy right here, which only has 1. This thing right here, this molecule right here can form resonance structures. If this bond were to move here, it could push this guy over here. It has resonance, which means it's more stable. This guy right here has 2 bonds, but they are not close enough to be resonance structures. This guy right here is the least stable, which means you would have the highest heat of hydrogenation, which this guy right here is true. This guy right here is the least stable, which means we'd have the highest heat of hydrogenation. So that right there, it is between cis and trans. Now, in regard to double bonds, cis molecules are less stable than trans molecules. The reason being is if this bond would disappear, this guy would be available to bond with, and this guy right here would be able to bond with. If 2 big molecules, for example, like bromine, were to attach to this molecule, that they would be competing with each other, and that's a no-no. So that's where you have to have a wedge and a dash come in. With trans molecules, it's much easier because they're not next to each other. So molecules can attach much easier, less likely to have recent mixtures and such. So this one right here is false because it should be this guy, then this guy, and then this guy. Okay, second one down here. This guy right here is going to be, oops, yeah. This third one right here is going to be false as well. I'll show you why. This right here is an example of a cis structure, or tri-substituted structure. This is a monosubstituted structure, and this right here is also a monosubstituted structure. This guy right here, though, is way more stable because it can put its positive charge here and its negative charge somewhere else. This guy right here is a little less unstable because it's part of the ring structure. That's why this is false. This guy right here is true because this guy right here has 2 double bonds, while this guy has 1. Even though these guys could form resonance, they're too close to each other. So still. Going on here, this last one here is also going to be false. This guy right here is the most stable. He should be at the very end because he can form resonance structures. So this right here is false. We don't see that. This bond goes here, which moves all these bonds, or this bond goes here and messes all the other bonds up. Okay, this guy is a little weird. The best way that I can tell you how to do this guy is to ignore this hydrogen right here. If you ignore that hydrogen, things will make sense. So I got a double bond. We're going to move the electrons. Electrons are going to go up to here, make this guy slightly negative, which will make this guy right here slightly positive. The electrons on my oxygen will attach to that slightly positive guy right here. So, bada bing, bada boom. There we go. Now this guy right here is slightly negative. This guy, I'm gonna the hydrogen here. If we ignore, or we take this bond right here towards the oxygen, make oxygen's positive charge go away. this free floating hydrogen then can bond to this guy right here, thus making it kind of happy. And the final structure should look something akin to that. Okay. Now, this is not an addition question because there is no second solvent or something like that. This means that this guy right here, this guy right here is going to be an E1 reaction. E1 reaction. So when this guy right here leaves, a good leaving group, and we're going to take the hydrogen away from this guy right here. So we're going to get this double bond with this methyl group going down. Now, hopefully you guys remember your chart for share diagrams. If not, you only have three possibilities: 1, 2, 1, 3, 1, 4. If it is equatorial, axial, or axial equatorial, this right here would be cis, this would be trans, and this would be cis. If you have equatorial, or axial, you would have trans for 1, 2, and trans for 1, 4, and cis for 1, 3. Since right here we have 1, 2, 3, 4, we're doing 1, 4. One is axial, one is equatorial. They are going to be cis of each other. So both can be wedges or both be dashes. And that's how you would do that one. This chart right here is needed for Grubbs because Grubbs likes stereochemistry. Go 2 points away. It's not. Okay. Remember, NBS is going to add a bromine to the most substituted carbon. So let's draw our cyclopentane. And since they're double bond here, the most substituted area would be this guy right here, would be this guy right here, and the bromine would be attached right there. The bromine would be attached there. It is not going to be racemic because it is not chiral. The reason why it's not chiral is here and here are both CH2 molecules, so it would not work. So not chiral. Okay. Over here, what's going on right here is I got to make these two guys, which means I need to kick off the hydrogen. So the oxygen is going to get one, and this amine right here is going to pick up a hydrogen, which is going to be 2 arrows. So I'm going to go a little quicker because my next class is starting. I want to make sure I get this done for the next class begins. What's going to happen here is one of the bonds on the sulfur is going to go towards it, making it slightly negative, making the carbon positive, which the oxygen is going to be attracted to. 2 arrows. From here, you notice that right here, the I leaves, that's 1 arrow. This negative charge in the sulfur attaches to this methyl group, which is what this guy right here is. That's 2 arrows. So far we're at 6. So right there, 6. And then lastly, I don't know, let's see, purple or blue. I need to make this guy and this guy. So what's going to happen is the oxygen is going to leave. Oxygen to take its double bond. It's going to go here. That's going to occur. We're going to move the bond here. It's going to be slightly negative here. The H is going to pop off and go towards it. So we have 3 arrows. I would argue 4 arrows, but Grubbs says it's 3 arrows. This is the problem with arrows and Grubbs.